All right, so this is E45, which is our applications of exponential and logarithmic functions. And really the only types of problems we're going to do are models of population growth, which is talking about when the rate of the growth of a population is proportional to the size of the population. Okay, that's when we get exponential growth. Okay, and we use the functions listed here on page 1 for both exponential growth and exponential decay. So if you notice, there's a little explanation of everything. But if you notice, this function and this function look almost identical. The only difference is this little bitty negative here in the exponent. Okay, if it's an exponential decay, meaning over time, we are decreasing the amount of the population or the amount of the material or the amount of whatever it is we're talking about, then if you look at the graph below, obviously this is going to be a decreasing function. In order for it to be a decreasing function, that means that our rate should be negative, right? Or it should be decaying. So that's why there's a negative on this second function. On the first function, when we have exponential growth, notice if we like invest money, or if we're talking about, I don't know, the breeding habits of rabbits or something of that sort, that's something that's going to grow exponentially. So if it's growing, our little growth rate k here would be positive, which means that it's going to be an increasing function. Now for your homework, I'm not going to have you graph these functions or your findings or the results, okay, but I just wanted you to have an idea of, these are functions that we have dealt with before, because these are just exponential functions, okay? So I'm just going to go ahead and outline what all these little variables mean. P of t is our ending amount. Okay? That's how much we want to end up with at the end. Okay, so if we talk about a doubling time, we want to have twice what we started with. If we have a specific amount that we want to end up with, that's where we would put it, is on the left side of the equal sign. Okay, our P sub 0, or the way we say that is P naught, P sub 0, is our initial amount. Okay, so if they don't tell us our initial amount, we can assume that we're starting out with 100%. Like if we talk about how much of a certain material is left in our body after we die or something like that, we can assume that, on the day we died, we had 100% of that material, and then after years and years and years, if it decays or if whatever, we can do it in terms of percentages. Most of the problems will give us a starting amount, and then we figure out the ending amount or something of that sort. But if one's not given, we can always assume the initial amount is 100% unless otherwise specified. Okay, and then our K is always our rate. Okay, again, if it's a growth rate, it's positive. If it's a decay rate, it's negative. And then T is our time. Okay, and the same holds true over here for the decay rate function. Okay, all of the P of t, P naught, K and T all stand for the same thing. Okay, I've had several people ask me what the E is. Okay, the E is the E button on your calculator. You should have a button that looks like E to the X, or just E. Okay, this is the E button on your calculator, which for some reason, anytime we deal with exponential growth or decay rate, it's an exponential function with base E. Okay, so don't let the E freak you out. It's just the E button on your calculator. Do not approximate E. E is like 2.71 and some more decimal places, but don't do that. When you're solving anything that has an E in it, make sure you use the E button so that you get the most accurate answer. Okay. The other thing I want to point out is we can also use this model, right? The P of t is equal to P naught E to the KT for continuous compounding. So I'm just going to say also used for continuous compounding. And what that is referring to, excuse me, is like investing money. Okay, if it's continuously compounded interest, we use this equation. Okay, and usually we use rate when we talk about money. So I'm just going to put here where K is equal to R and R is our rate. Okay, so anytime they talk about rate, we usually use an R, but since we're doing continuous compounding money problems in this section, and remember K is always our rate. So don't let the R and the K confuse you. It's just the same thing. They both represent the rate, whether it be an interest rate, a decay rate, a growth rate, anything of that sort. Okay, so let's just go ahead and jump in and look at an example. This first one says the population growth of Mexico. So in 2011, the population of Mexico was about 113.7 million, and the exponential growth rate was 1.1% per year. Okay, now the first thing it says is find the exponential growth function. So because we see exponential growth function, we know we're using the function with the positive k. So I'm going to go ahead and just write down here what our generic function looks like is p of t is equal to p naught e to the kt. So this is the function we want, but we want it specific to our problem. So in order to make it specific to our problem, we need to know our initial amount, okay? And then we also need to know our growth rate, or our decay rate, growth rate in this case. So looking at this problem, if I read through it, notice they gave me both of those. They told me that my initial amount, or my initial population in Mexico, was 113.7 million. Okay, and then they told me that my growth rate was 1.1%. So that means K is 1.1%. Now, anytime we plug in anything into our formula, we never use percents. We always write them as decimals. So to move a percentage into a decimal, we move the decimal place 2 places to the left. So we'd end up with 0.011 as our rate. Okay, so now I just want to go ahead and rewrite this function. So that means our exponential growth function looks like P of t, or our population at time t, is equal to our initial amount, 113.7, times e to our k, which is 0.011 times t. So if we want to know any time, if we have any time, we can plug it into this and figure out what the population of Mexico should be. Or if we want to figure out how much time it will take for the population of Mexico to reach a certain amount, we could put our ending amount over here and then solve this for t. So once we have our function, that's the important thing. Once we have our function, now we can either put in a time to figure out the end population, or we can put in an ending population to figure out the year in which that will happen. Okay, so let's go ahead and see. The second one, part B, says estimate the population in 2015. So if you notice, in our original problem, okay, it says in 2011. So our starting point, or our point of reference here, is in 2011. And they're asking me about 2015, right? If I'm looking for 2015, I need to know what time am I plugging into my function? How much time has passed? So all I have to do is the year 2015 minus the year 2011, which is a difference of 4 years. Okay, this is the time that I'm plugging in, and I plug it into the function I found in part A. So I want to know what's the population at time equals 4. So I get 113.7 times e raised to my constant, which is 0.011, times my time, which we're plugging in 4 years. And then I just simplify. And when I simplify, I do simplification in the exponent first. So I have 113.7 times e to the 0.044 when I multiply my exponents. And then in your calculator, you want to go ahead and do e to the 0.044 power, which should give you something like 1.044 and a whole bunch of other decimal places. Now, never round until the final answer. So I'm going to go ahead and multiply this number by 113.7, which gives me 118.814 and some more stuff. Now in this problem, it didn't specifically tell me how to round. In your problems on My Math Lab, it will tell you how many decimal places to round each piece to. So for this one, I'm just going to go ahead and approximate it. So this is approximately 118.8. I'm just going to round to 1 decimal place. Okay, and notice what we're finding is the population in Mexico in the year 2015. So this means there should be 118.8 million people living in Mexico in 2015. Okay, so part C is going to ask us to find something the other direction. Instead of giving us a time and asking us for the population, they're going to give us a population, and we have to figure out how much time until we reach that population. So here it says, how long would the population be double what it was? I think this is supposed to be will. Sorry, typo. How long will the population be double what it was in 2011? Okay, so we know what it was in 2011. In 2011, it was 113.7. So in order to double that, I just multiply it times 2. So to double that, that would give me, let me see, 227.4. So that's our ending amount. Okay, so we want to know in what year do we get 227.4 million people living in Mexico. So I'm going to plug that into the left-hand side of my equation since that is my ending amount. So I'm going to go ahead and do 227.4 is equal to my initial amount, 113.7, times e to my constant, or my, I'm sorry, I keep saying my constant, my growth rate, which is 0.011, times my time, which we don't know. That's what we're trying to figure out here. Okay, so notice my unknown is inside an exponential function. If it's inside an exponential function, I must first get that exponential function isolated. So I'm going to go ahead and divide off my 113.7, which gives me 2 is equal to e to the 0.011t. And then to get rid of e, remember we learned this when we went over exponential functions, we take the inverse of e, which is a log base e. And remember, log base e is ln. So I'm going to take ln of the left-hand side and ln of the right-hand side. And the reason I'm doing this is so that ln and e will cancel. So I have ln of 2 is equal to 0.011t. And then the last thing I have to do is just divide off my 0.011 so that t is isolated. Okay. And then from here we can do this in our calculator. ln of 2, get an answer for that, and then divide it by 0.011, and we should get something like 63.013, ... keeps going. And then again, we're approximating our time. In your homework, it'll tell you exactly how many decimal places to round it to, or it might say round it to the nearest year, or round it to the nearest tenth of the year. So make sure you pay attention to your instructions. Here I didn't specify in my notes, so I'm just going to round it to the nearest year. So I'm going to say it's going to take approximately 63 years for our population in Mexico to double what it was in 2011. Okay, not too bad, hopefully. Notice on this one, they gave us the initial amount and our k value in the problem. So that was awesome. We got our function right away, and then we could start solving. On the next two examples, they're not going to give us our initial amount and or our growth rate. We have to figure that out. Okay, so let's look at another one. This one is talking about carbon dating. It says the radioactive element in carbon-14 has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? And it says, hint, you first need to determine the value of k. Okay, we just read a whole lot of stuff. We need to pick out what's important. Usually the first sentence will give us everything we need to know. Okay, first we see carbon dating. If we're talking about carbon dating, we're talking about really, really old things, and the amount of carbon is going to be getting less and less and less. Okay, so what we want to do is we want to go ahead and because this is exponential decay, I'm going to go ahead and write that down. Exponential decay, then we're going to use the P of t equals P naught e to the negative kt, because the carbon should be decreasing, or the amount of carbon should be decreasing over time. So this is the formula we're going to use. Now, in order to find this formula, I need to know my initial amount, and I need to know my constant, which they didn't actually give me. The only thing that they told me was a half-life, and then they told me that these scrolls they found had lost 22.3%. Now, that's not saying that's the rate. It didn't say that was my rate. That just said that's how much they lost. So that I can't use. So I'm going to get everything I need from this first sentence. This first sentence says, an element has a half-life of 5750 years. Okay, a half-life means whatever you started out with, you ended up with half that amount at a certain time. Okay, so what we're going to go ahead and do is I'm going to go ahead and assume that we start out with 100% of our carbon. Okay, so I'm going to go ahead and say here that P naught has to be 100%. Okay, and then because we're talking about a half-life, that means that we're ending up with 50%. Okay, so that's going to be my ending value. My ending value is going to be 50%. Okay, and they tell me that the half-life of a radioactive element, carbon-14, is 5,750 years. So that gives me my T, 5750 years. So I'm going to plug all this in, and notice the only thing that I don't have a value for is K. So I'm plugging everything in so I can solve for my K, and then once I know K, I can use that and my initial amount of 100% to write my function. So let's go ahead and say my ending amount is 50% is equal to my 100% of carbon that I started out with, e to the negative k, which we don't know what k is, times my time, which is 5750. Now, two things I'm going to do. One, I'm going to write my percentages as decimals. And two, in the exponent, I'm going to go ahead and multiply negative k and 5750. So 50% as a decimal is 0.5. 100% as a decimal is just 1. And I have e to the negative 5750k. So if I multiply negative k by 5,750, I get negative 5,750k. Now, 1 times e is just e, right? Or I can think of like dividing off the 1. You don't actually have to do this because 1, you can write it or not write it. So I have 0.5 is equal to e to the negative 5750k. And then I need to get k by itself. It's in the exponent, which means I need to get rid of my exponential base, which in this case is e. To get rid of e, I use ln. So I'm going to do ln of 0.5 on the left is equal to ln of e to the negative 5750k on the right. I do this so that my ln and my e will cancel, okay, which leaves me with ln of 0.5 is equal to negative 5750k. And now all I have to do is divide off my negative 5750. Okay, I know these numbers are ugly, but as far as the math itself, this shouldn't completely frustrate us, hopefully. So here we get k is, if I do ln of 0.5, we should get something like negative 0.693. Again, leave all your decimal places. If you have a very basic calculator, you might want to use your store function. Okay, so you can store and recall these numbers without losing decimal places. All right, so when I divide these, I should end up with like 0.000120547. In my math lab, it will tell you exactly how many decimal places to keep of k. But for this example, I'm just going to go ahead and round it to the 5th decimal place because the next one's a 0 and it's a good cutoff point. So I'm going to say k is approximately 0.00012. Okay. So now that I know my k, I should be able to write my function for this decay model. So I'm going to go ahead and rewrite. This is just going to be P of t is equal to P naught. Now here, again, they did not give me an original amount because we assume whatever carbon is inside the object, right, they start out with 100% of it. So I'm going to let my initial amount be 100%, which again I'm going to write as a 1, e to the negative k, so negative 0.00012 times time. Okay, so here, this is my function that I'm going to use to now figure out what they're asking me. So they give me another sentence that says, you know, the percentage of carbon-14 present tells us how old the age of the organic matter was. Okay, we don't care about that sentence. What we care about is the next sentence, which says, archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% at the time it was found. Okay, so remember, when we plug things into our function, whatever P of t is, that is our ending amount, right? So here, if, let me go ahead and do this so you know we're working a new problem. If we know that it lost 22.3% of its carbon, we need to know how much does it have. What is its ending amount? So if we take 100% and subtract the 22.3% that it lost, that means that our ending amount is 77.7%. Okay. This is our ending amount. So what we're going to go ahead and do is plug in the 77.7% and figure out what time that happened at. Because once we know the time, that will tell us the age of the Dead Sea Scroll. Okay. So again, if I plug in, excuse me, my ending amount, which I'm going to write as a decimal, so 0.777 is equal to, I'm just plugging this into my function that I wrote right up here, 1 times e to the negative 0.00012t. Okay, so I figured out what my ending amount is, and now I'm just plugging my ending amount into the function that I found first. Okay, and now here I can just solve. Again, I don't really need to divide off this 1 because 1 times e to the mess is still just e to the mess. So I'm going to go ahead and take ln of both sides. Ln of 0.777 on the left, ln of e to the negative 0.00012t on the right. Ln and e will cancel, which leaves me with ln of 0.777 is equal to negative 0.00012t, and then I just divide off my negative 0.00012 to get t on one side all by itself. Okay. So that means that t is approximately, again, you can do this in steps if you want. You could do ln of 0.777, which should give you approximately negative 0.2523 and a whole bunch of other stuff. And then divide off the 0.00012. If your calculator can do it all in one step, that's good. Remember, you cannot use a graphing calculator on your exams. So make sure if you have been using one that you know how to do this on a scientific calculator, which is what you'll be using on your final. Okay. All right. When I divide these, I get something like 2102.62 and some more mess. And if you remember, we're trying to figure out the age of the Dead Sea Scrolls, about how old they are. So this is time. So again, I'm going to go ahead and round it to the nearest year. So this means that those Dead Sea Scrolls that were found with only 77.7% of their carbon-14 remaining had to have been about 2,103 years old. Okay. All right. I'm going to look at one more, and then I'm going to give y'all some to do. I want to look at one more example where we have to figure out K by ourselves first in order to get our interest rate. Okay. This is talking about compounded interest continuously. Okay. So anytime we do that, we're assuming that it's going to be grow. Okay. So as it grows to a certain amount, we would hate to think that we would put our money in a bank and it would decay, correct? That would not be good. So we're going to go ahead and use our P of t is equal to P naught e to the kt with a positive k. Now that we know what function we're using, the first thing it asks us is what is our interest rate? So that means it's not given to us. So let's go ahead and read our problem. It says, suppose, let me go like this here. Suppose that $2,000 is invested. Okay, so if that's what's getting invested, I'm going to go ahead and write up here. That's going to be our P naught. That's our initial investment. At an interest rate K, compounded continuously, and grows to $2,504.65. So that's our ending amount. So I'm going to go ahead and write that's P of t. That's how much we want to end up with. And we want to end up with this in 5 years. So that's my time. Okay. What is my interest rate? So for part A, I'm just taking all those pieces I know and plugging them into this function. So my ending amount is 2504.65. I set that equal to my initial amount, which is 2,000, times e raised to the k, which we don't know, times t, which we do know is 5. And now I need to solve for k. So I need to get my exponential base isolated. So I go ahead and divide off the 2,000. Okay, 2504 divided by 2504.65 divided by 2,000 gives me something like 1.252325, and I think it keeps going, equals e to the 5k, or k times 5. I like to write it correctly. And then I need to take ln of both sides to get rid of that e. Okay, 252325, keeps going, equals ln of e to the 5k. So notice on the right hand side, my ln and my e will cancel. On the right hand side, or the left hand side, I have ln of 1.252325. Again, when you first got that number, hopefully you just left it in your calculator, because now to solve for k, all I need to do is divide off that 5. So I would go ahead and take ln of that number, divide it by 5, which should give us 0.04500 and some more stuff. Again, on my math lab, if it asks you to find the interest rate, it will tell you exactly how many decimal places to keep. I'm pretty sure most of the time we keep 4 decimal places. Okay, so I'm going to go ahead and keep 4 decimal places on this one, just so that you're used to that. Here we don't really need to, because our 4th decimal place obviously is a 0. But I'm going to go ahead and write that k is approximately 0.0450. Okay, so that's our interest rate. So notice for part B, the next thing it asks is find the exponential growth function. So now that I know what my k is, in order to find my function, okay, I use my generic function here, kt, and I just plug in my initial amount and my k value. Okay, so that means I have p of t, or my investment at times t, is equal to my initial investment, which is 2,000, times e raised to the kt, and we know k is 0.0450t. So now I have my function. Once I have my function, I can now solve for whatever they want me to. So they can either give me a time and I find the amount of money, or they could give me the amount of money and I find the time it takes to get that amount. So I'm going to go ahead and scroll back up so I can see what it says. Part C says, what will the balance be after 10 years? Okay, so I'm going to just plug in. When it gives me 10 years, that means that's giving me the time. So they want to know, how much money do I have when t equals 10? So I'm going to come down here and I'm just going to plug p of 10 in. So that gives me 2,000 e to the 0.0450 times 10. And now all I have to do is simplify the right hand side. First thing I do is multiply out my exponents. That gives me 0.4500, right? Or we could drop the zeros. And then I'm going to do e to that power. When I raise e to the 0.45 or 0.4500, I get 1.5683, and it just keeps going. And then I multiply that by 2,000, which gives me 3136.6243 and some more stuff. Now remember, we're trying to figure out how much our investment is worth after 10 years. So since we're talking in money, I want to go ahead and round it to 2 decimal places. So I'm going to say after 10 years, we have approximately $3,136.62. Please pay attention to the instructions in my math lab, because it may say round to the nearest dollar. Okay, if that would have been our instructions here, we would have just rounded it to 3137. If it doesn't tell you to round to the nearest dollar, then anytime you're dealing in money, you can assume you need 2 decimal places. Okay, all right, let's look at our last one. Part D. Part D says, after how long will the 2,000 have doubled? Okay, so to double 2,000 means we now have 4,000. So we want our ending amount to be 4,000. So I'm just going to go ahead and put 4,000 in on the left-hand side of my equation, because that's my ending amount, is equal to my initial amount, which is 2,000, e to the kt, where my k is 0.0450t. So I divide off my 2,000 to get e isolated. When I divide off my 2,000, that leaves me with just 2 is equal to e to the 0.0450t. Then again, I take ln of both sides to get rid of that pesky e. And when I do that, my ln and my e will cancel on the right-hand side. So I'm left with ln of 2 is equal to 0.0450t. And then I just divide off the 0.0450 off of each side to get t completely isolated. Okay. So this means that t is equal to, when you get a decimal for this, it's something along the lines of 15.4032 blah blah blah. Okay. Again, we're wanting to know how long will it take to double our initial investment, or to double our $2,000. So we're solving for years here. Again, it may ask you to round to the nearest year, round to the nearest tenth of a year. So make sure you read your instructions. I'm going to go ahead and round it to the nearest tenth just because I have a 0. So I'm going to go ahead and say 15.4 years. Time is approximately 15.4 years. Okay? All right. So I have given you 2 practice problems. And I'll give you just a minute to go ahead and go over those, and then we'll go over them in detail. All right, so on this first one, notice it says the Houston Sugar Land Baytown metropolitan area is the 5th largest metropolitan area in the U.S. And 2010, the population was 5.9 million, and the exponential growth rate was 1.76 per year. First, they want you to find the exponential growth function. So this is good because they gave you the rate and they gave you the initial population. So all you have to do is plug that into your function. So notice here on part A, I just plugged in 1.76%, which as a decimal is 0.176. And then I plugged in my initial population, which was 5.9 million. Okay, so my growth rate function is P of t is equal to 5.9 e to my k, which is 0.0176, times t, which is my time. Okay, part B says estimate when the population, estimate the population in 2016. So first I need to know how much time has lapsed. So my initial population, 5.9 million, was referenced in 2010. So I take 2016, which is what they want me to find, subtract 2010, which means I have 6 years that have lapsed. Okay, so my time is 6, so I'm plugging 6 into the function that I got in part A. Notice when I do that, I just multiply 6 times 0.0176 in my exponent. I raise e to that power, which gives me 1.111 and some more stuff. And then I multiply that by my initial amount, which was 5.9. That gives me 6.557. I went ahead and just rounded it to 1 decimal place. Again, if you got the same answer and rounded differently, that's fine. Just make sure you pay attention on your homework that you round correctly the way they want you to. Okay. All right, part C says, when will the population be 7 million? So they're saying 7 million is our ending amount. So we set the function equal to 7 on the left-hand side, and then we just solve. First thing we do is get rid of our coefficient on our exponential base, which is the 5.9. When I divide that off, make sure you leave all those decimal places in your calculator. So we get 1.186 and a whole bunch of other mess is equal to e to the 0.0176. Then we take ln of both sides to get rid of the e. And then it's just simplifying our calculator. Okay. And then divide off the 0.176. Okay. Once we do that, we can go ahead and assume that it's roughly 9.7 years it will take in order to reach 7 million. Okay. And then the last part, part D, is kind of the same idea. All right, so on part D, it's asking me to find the doubling time. So I start out with my initial amount in 2010, which was 5.9, and they want to know how long will it take to double that. So I take 5.9 and multiply it by 2, or double it, right? Oops, let me scroll down. Which would give me 11.8. So I put in 11.8 as my ending time, or my ending amount. Set that equal to my function, which is 5.9 e to the 0.0176t. I divide off my coefficient, which is my 5.9, which gives me 2 is equal to e to my constant times my time.
I take ln of both sides so that my e will cancel, which gives me ln of 2 is equal to my exponent from the right-hand side, which was 0.0176t. And then I just divide off that 0.0176, which I worked it out here and got 39.383 and some more stuff. So I went ahead and rounded it to 1 decimal place. Again, you want to do whatever my math lab tells you. So it'll take roughly 39.4 years in order for our population to double here. Okay. All right, let's look at the second one. The second one is talking about U.S. exports. It increased from 12 billion in 1950 to 1,550 billion in 2009. So they want us to find the value of K and write the function. So what I'm going to do is we need to know what our initial amount was, what our new amount was, and how long it took us to make that difference. So I'm going to go ahead and start off by taking 2009 and subtracting 1950, which gives me 59 years. So it took 59 years for it to increase that much. Now because it's increasing, I'm going to use the growth function, which is the one with the positive K. The other thing I need to know is my ending amount and my beginning, okay? Since my beginning amount is in billions, I'm going to do the whole thing in billions, okay? So my ending amount is 1550 billion is equal to my initial amount, which here is 12, e to the k times my time, which is 59. To solve for k, I divide off my 12, leave all your decimal places. I take ln of both sides to get rid of my e, and then once my e is gone, I can divide off that 59. Okay, so I got a decimal for k, which is approximately, again, I'm just going to use 4 decimal places here because I think that's what they do on my math lab. So my k is 0.0824, and then they want me to write the function. So I write my growth function again, but this time putting in my specific initial amount and the growth rate specific to this problem. So it looks like P of t is equal to 12e to the 0.0824t. So now I have my function. Now they're going to have me do something with it. So this function represents the amount of money, right, or our value of exports based on the year. So they're either going to give us the value and we have to figure out what year that happened in, or they're going to give us the year and we figure out the value earned in that year. Okay, so on part B it says estimate the value of exports in billions in 1972, in 2001, and in 2015. Round to the near, oh man, I have typos, I apologize. Round to the nearest tenth of a billion. So down here, notice I went ahead and just wrote my function up here at the top. Okay, this is the function we got from part A. And then once I have my function, then I just need to figure out what my time is for each of these years. So I always subtract from my my initial time, right, or my start value. So here, my earliest time in this problem was 1950. So if they want to know the value of exports in 1972, I take 1972 minus 1950, which gives me 22 as my time, or 22 years it has passed. Once I know my time, I just plug it into the function I have highlighted here. And simplify on my calculator. So I have worked out all 3 of these. In 1972, there was a value of 73.5 billion in exports. In 2001, your time should be 51, and there was 802.2 billion value of exports. And then in 2015, you should get 2,542.5 billion. Okay. All right. So there's one more example I want to show you. And then you should be able to do this homework. Okay, go back over here to the blank one. All right, so this last example I want to go over is talking about present value. And really, this is exactly like all the other ones we've done. The only difference here is the thing you're solving for is not the ending value and it's not the time. So this is just another example of something they could throw your way. So this says, following the birth of a child, a parent wants to make an initial investment, P0, that will grow to $50,000 for the, oh my goodness, with my typos. Well, you probably know what this should say, but it should be for the child's education at age 18. Interest is compounded continuously at 7%. What should the initial investment be? Such an amount is called the present value of $50,000 due 18 years from now. So this is just wording that we don't necessarily care about. All right, so what's happening is somebody had a baby, and by the time they're 18, they're hoping they have $50,000 for this kid's education. So they want to know how much money initially do they need to start off with in order for this to happen. So assuming we invest money and it grows, we want to use the exponential growth function, right? So we are hoping that our money increases. So we're going to go ahead and use P of t is equal to P naught e to the kt with a positive k because we want it to grow. All right, so we're going to go ahead and plug in everything that they gave us and figure out what we're missing. Okay, so again, I'm just going to go ahead and write over here. Let's see. P naught is what we don't know. So we don't know what that equals. Our ending amount, P of t, we want it to grow to $50,000, right? Our constant, or the rate, it says 7%. And remember, we write that as a decimal. So 7% as a decimal would be 0.07. And then, let's see, what else we need to know? And then our time. Our time would be 18. Because when this kid hits 18, that's when we hope he goes to college, he or she, and that's when we'd like him or her to have $50,000. So we're going to go ahead and plug everything in and then solve for P naught. So our ending amount is $50,000 is equal to our initial investment, which we don't know we're solving for, e raised to the k, which is 0.07, times my time, which is 18. And now we just solve. Okay, I'm going to go ahead and simplify by multiplying the values in my exponents. So I have 50,000 is equal to P naught e to the 1.26 when I multiply those two numbers together. And then, excuse me, in order to solve for P naught, I just need to divide off this e to the 1.26. And it doesn't matter if you simplify e to the 1.26 first and then divide it off, or if you divide it off and then do it in the next step. Either way is fine. Okay, so this means that P naught is equal to 50,000 divided by e to the 26, which if you do that on your calculator should be roughly 3.5254 blah blah blah. Again, leave all the decimal places in your calculator. So when we multiply this out, we should get something like 14182.70133 blah blah blah. Okay, so this is what our initial investment should be. Now, unless they tell you to round it to the nearest dollar, we go ahead and because it's money, we round it to 2 decimal places. Okay, which means that our initial investment should be roughly $14,182.70. Okay, which is what every new parent has lying around, right? That's a chunk of money to dish out when you have a newborn. But if you do, apparently, and you invested at a 7% interest rate, you could have $50,000 by the time your kid's 18. All right, so that is the end of the 4.5 lecture. You should now be able to complete the My Math Lab 4.5 assignment. There is no worksheet on this one. Please let me know if you have any questions.